4.2 Lesson 1, Derivative of a product of two functions. Objectives. You will understand the proof of the differentiation rule for finding the derivative of a product of two functions called the product rule. You will remember the product rule, and you'll be able to use the product rule to find the derivative of a product of two functions. We will begin thinking about how to find the derivative of a product of two differentiable functions f and g. If you have y is equal to f of x times g of x, what is y prime? We want to begin by emphasizing that y prime is not f prime of x times g prime of x. Why not? Let's look at an example for why this is not the case. Suppose you have y and it's the product of x to the fifth times x to the eighth. So x to the fifth would be f of x, and x to the eighth would be g of x. Each one of these two functions are differentiable because they're just power functions. I know how to find the derivative of a power function. I use the power rule. So I can find f prime of x and g prime of x. This is what we've learned before. But the question is, how do you find the derivative of y is equal to x to the fifth times x to the eighth? The answer is, it is not f prime of x times g prime of x. And we want to see why this is not the case. Y prime is not f prime of x times g prime of x. It is not 5x to the fourth times 8x to the seventh. It is not 5 times 8 is 40, and 8x to the fourth times x to the seventh is x to the 11th. It is not this particular function. Why not? Consider this. Suppose you begin with the function that y is. It's the product of these two differentiable functions f and g. But instead of doing what we did here on the bottom right side of our screen, suppose you begin by multiplying f and g before differentiating. So you have a product of two powers with the same base, so you can add the exponents. 5 plus 8 is 13. So now you have a power function, so using the power rule, the derivative of this power function is 13 times x to the 12th. And you can see that that is not the same as what we had earlier. That is why this cannot be correct. So the bottom line is, if you have y as a product of two differentiable functions f and g, y prime is not f prime of x times g prime of x. It is something else. What is that rule for finding the derivative of a product of two differentiable functions? It's called the product rule, and we will see what the product rule is and why it's true now. Now we will look at Objective 1. You will understand the proof of the differentiation rule for finding the derivative of a product of two functions called the product rule. And then once you know what that is, you will have to remember it and then be able to use the product rule to find the derivative of a product of two functions. Here's a proof of the product rule. There is also a proof of the product rule that is provided in your textbook. It is done with a different approach, a slightly different approach, using different notations, etc. But it is a proof just like what we're looking at here, just done differently. So let's take a look at an alternative way you can prove the product rule from a different textbook. So what is the product rule? So here we have the product rule, the product of two differentiable functions f and g. So if you have y is equal to f of x times g of x, and each of these two functions are differentiable, meaning f prime of x exists and g prime of x exists, then how do you find the derivative of the product of f and g? The product of two differentiable functions f and g is itself differentiable. The derivative of the product is the first function times the derivative of the second plus the second function times the derivative of the first. Why is this true? The proof shows us why this is true. But I'd like to also, before we look at the proof, I'd like to show you that this differentiation rule can also be written as follows. The derivative with respect to x of the product of two differentiable functions f and g can also be written as, look at this term here. Now notice that you have a sum, and of course if you have a sum, we know that addition is commutative, so you can write the second term first and the first term second. So we're going to do that. So we're going to write g of x times f prime of x first. And in fact, we're also going to write that product, g of x times f prime of x, as f prime of x times g of x. And then we have plus, and we're going to write f of x times g prime of x. So it's the same thing, just the two terms have been rearranged, and I rewrote this particular term where I switched the factors g of x and f prime of x. The point that I want to make is that this is exactly the same as what you see here. But this is a little bit easier to remember, and here's how you're going to remember this, because you need to remember the product rule. So you have a product of two functions f and g. We'll call f the first function because it's written first, and we'll call g the second function because it's written second. According to the product rule, the derivative of a product of two differentiable functions f and g is the derivative of the first function times the second plus the first function times the derivative of the second. It's a little bit easier to remember writing it in that particular form, and you have the words to go along with that. And this is the version of the product rule that is given in your textbook. You can see verbally the derivative of the first function times the second plus the first function times the derivative of the second. That is the product rule. So we will take a look at the proof of the product rule so that we understand why it's like this and not f prime of x times g prime of x. But before we look at that, let's go back to what we had started with. So we know the product rule is not f prime of x times g prime of x. And now we see that the product rule is the derivative of the first function times the second plus the first function times the derivative of the second. In fact, for the example that we started with, demonstrating what the product rule is not, we know the correct differentiation rule is 13 times x to the 12th. So let's see if we can get that by using the product rule. So we're going to use gold, and we have y is equal to x to the 5th times x to the 8th. So according to the product rule, y prime would be the derivative of the first function, which will be 5x to the 4th, times the second function, plus the first function times the derivative of the second function. The derivative of the second function would be 8x to the 7th. So we have y prime is equal to, you have a product of two powers with the same base, so you can add the exponents and you get 5 times x to the 12th, plus, here you have a product of two powers with the same base, so you have the constant 8, and then you have a product of two powers with the same base. X to the 5th times x to the 7th will be x to the 12th. And what you have here are two like terms. You have 5 times x to the 12th plus 8 times x to the 12th. So when you combine the like terms, you get 13 times x to the 12th, which is, of course, what we had here. So this is, in fact, the correct derivative. It agrees with the product rule, but as we saw earlier, you cannot just multiply the derivative of the first function by the derivative of the second function. This is incorrect, what you see at the bottom of the screen on the right side. For a problem like this, obviously you don't really need the product rule. You could have done it like we did here, but there are other problems where you would need the product rule, and we will see a couple of examples after we take a look at why the product rule is true. So now we will go ahead and take a look at the proof of the differentiation rule for finding the derivative of a product of two functions called the product rule. The most important thing that I want you to understand about this proof is the very first line, the beginning of the proof. What is this? It's the definition of the derivative as a function. What do we mean by the derivative of a function? We mean this limit of a difference quotient as delta x goes to 0. So when you want to prove the product rule, you have to begin with what a derivative is. This is what we mean by a derivative. So we will begin with that in the proof of the product rule. So our function is f of x times g of x. So in the difference quotient, you have three parts. The denominator is just delta x, so we have that. And in the numerator, we have minus f of x, so minus the function, we have that. And then here we have the function evaluated at x plus delta x. So our function is f of x times g of x, so we have that evaluated at x plus delta x. So we have f evaluated at x plus delta x, and then we multiply that by g evaluated at x plus delta x. And then we take the limit of that difference quotient as delta x goes to 0. Why do we do this? Because we're trying to find the derivative of this product, and this is what we mean by the derivative of a function. So that's why we do that. And this is the most important thing that I want you to understand from this proof, that this differentiation rule is proved using the definition of the derivative as a function. We'll go ahead and take a look at some of the other details. So what is done in the second line? You can read here in the description of the proof that some mathematical proofs, such as the proof of the sum rule, are straightforward. Others, such as this one, involve clever steps. This proof involves such a step, subtracting and adding the same quantity, which is shown in color here. So if you subtract and add the same quantity, it's like you're adding 0, so you're not changing what you have here, but you're just writing it in a different form that would allow you to further manipulate what you have algebraically and arrive at a conclusion at the end of the proof about what this derivative is equal to. So in the next line, here's what we're doing. You have this plus sign in the numerator, and of course you have division by delta x. So you can write that as a sum of two fractions, and each fraction will have a denominator of delta x. Furthermore, if you take a look at what we have here in the numerator of the first fraction, you can see that the two terms separated by this minus sign, they have a common factor of f of x plus delta x. So when we factor out f of x plus delta x, from the first term, we're left with g of x plus delta x, and then from the second term, we're left with g of x. And then we have the denominator of delta x, and you can write the f of x plus delta x, it would be over 1. So when you multiply it by what you have here, it is in fact the same as all of this. We do something similar for the second term. If you take a look at the numerator here, you can see that the two terms are separated by a minus sign. Each term has a common factor of g of x, so we factor out the g of x. From the first term, we're left with f of x plus delta x, and from the second term, we're left with f of x. And of course, there is the denominator of delta x, which you see here, and you can write g of x as g of x over 1, and when you multiply, it would be the same as all of this. So now we're here, and the next step is to recognize that here you have the limit of a sum. If you have the limit of a sum, you can write that as a sum of two limits. So that's what we're doing here. And then here what we have is the limit of a product. If you have the limit of a product, you can write that as a product of the limits. So that's what we're doing here. We write that as a product of these two limits. And we do the same thing here. We have the limit of a product, and we're going to write that as a product of the limits. To get to the very last line, consider the following. What do you see here? And what do you see here? You have the limit of a difference quotient, which has this form as delta x approaches 0. So in each case, you have the definition of the derivative of a function for the function g and for the function f. And since we're assuming that our product of f and g has differentiable functions f and g, the product of two differentiable functions is itself differentiable. So because we're assuming that the individual functions in our product are differentiable, these are derivatives of g and f. So this is just g prime of x, and what we have here is just f prime of x. So the only thing that's left is the limit as delta x goes to 0 of f of x plus delta x, and the limit of g of x as delta x goes to 0. You don't even see delta x here, so you just have g of x. And here you do see a delta x, but there's something in calculus that tells us, we haven't looked at this in this class, I don't think so, but if you have a function that's differentiable, and the function f is differentiable by assumption in our theorem, differentiability implies continuity, and if delta x is going to 0 for the continuous function f, if the input values are getting closer to x, then the output values will be getting closer to f of x, because f is a continuous function. So this limit is just f of x, and here we have the product rule. So that completes the proof of the product rule. So now you want to remember the product rule and be able to use it to find derivatives of products of functions. So we take a look at number 1 here, and you would recognize that the function that we have is a product of two differentiable functions. So to find the derivative, you have to use the product rule. You cannot do the following. This is not correct. Y prime is not equal to the derivative of x to the 5th times the derivative of sine x. It is not 5x to the 4th times cosine x. This is wrong. This is wrong. The correct way to find the derivative is by using the product rule. So you have y prime is equal to, the product rule says find the derivative of the first function and multiply by the second function and add to that the first function times the derivative of the second function. So to help you carry that out correctly, you can do this. You can use this notation. The derivative with respect to x of the first function times the second function plus the first function x to the 5th times the derivative with respect to x of the second function. So the derivative of the first function can be found using the power rule. Multiply that by the second function and add to that the first function times the derivative of the second function. The derivative of the sine function is cosine. So this is the correct derivative. You can simplify by recognizing that you have a sum of two terms, and there is a common factor of x to the fourth in each term, and you can factor out x to the fourth from each term. So from the first term, you'd be left with 5 times sine x, and from the second term, you'd be left with 1 factor of x times cosine x. And that would be the correct answer that has been simplified. This is the correct answer. This is not the correct answer at the bottom of the screen. So here we have number 2, differentiate and simplify. You should recognize that we have a product of two differentiable functions, so we need to find the derivative by using the product rule, and you will have y prime is equal to help you set it up correctly, the derivative of the first function times the second plus the first function times the derivative of the second function. So the derivative of the first function can be found by using the power rule. Multiply that by the second function and add to that the first function times the derivative of the second function. Observe here that the second function is a composition of two functions, where the inside function is 7x and the outside function is e to the x. So to find the derivative of the composition of two functions, you have to use the chain rule. So you multiply x to the 2.5 by the derivative of the second function. So you use the chain rule for that. You're going to find the derivative of the outside function evaluated at the inside function, and then multiply by the derivative of the inside function. The chain rule says find the derivative of the outside function evaluated at the inside function and multiply by the derivative of the inside function. So the derivative of the inside function is 7, so we have y prime is equal to 2.5 times x to the 1.5 times e to the 7x plus x to the 2.5. This is a 7 here, so we have 7 times x to the 2.5 times e to the 7x. This is the correct derivative. Now we can simplify by recognizing that we have a sum of two terms, and we can see if there are any common factors that we can factor out. So for example, both terms have a common factor of e to the 7x, and both terms have a common factor of x to the 1.5 power. So we can factor out x to the 1.5 power times e to the 7x, and from the first term we will be left with (2.5), so we write 2.5, and then from the second term we'll be left with 7 and x to the first. So this is our final answer. Today we looked at the product rule and we looked at the proof of the product rule. You need to remember the product rule, and we looked at about 3 examples of how to use the product rule to find the derivative of a product of two functions.